Welcome back once again to AI Citizenship for Medicine. This is our third lecture in the first series and is titled The Pitfalls of AI in Medicine. Today's lecture is extremely important as the principles we outline here will not just come into play throughout this course series, but also represent real threats to your patients, which you may be able to mitigate at various points in your career as an informed user of clinical AI. More concretely, our goals today are twofold. First, to provide a framework for describing the range of pitfalls that may arise when AI systems are introduced into healthcare. And second, to develop improved intuition for the nuanced and dynamic relationship between AI tools and the healthcare systems in which they operate. In doing so, we hope to support you in maximizing the benefits and minimizing the harms for your patients as you use AI throughout your career. To assess the potential risks posed by a medical AI system, it's helpful to take a comprehensive approach. One framework, which is actively used by the FDA, involves comparing the urgency of the clinical scenario in which the AI system is operating with the level of autonomy the system is granted as it operates. A table laying out these two axes is shown on the right. Systems that operate with minimal autonomy, only informing but not guiding clinical management, and do so in a non-serious clinical setting, such as a low-stakes outpatient setting, are naturally considered to constitute a fairly low risk level, level 1. In contrast, systems that have full autonomy to treat or diagnose, and do so in a critical healthcare setting, such as an ICU, pose the maximum potential risk in this framework. This sort of system we just described makes a lot of sense for regulators who need to think about what types of evidence of safety to require for a specific system, as well as potential safeguards to require be put into place at deployment time. But as medical practitioners, it's also critical that you develop an intuition for the different types of harms that may be posed by an AI system and their relative likelihood of occurring in your particular setting of practice. With all that in mind, this slide presents the framework which we will develop over the course of this lecture for discussing the potential pitfalls posed by medical AI systems. This framework is not exhaustive, but it does reflect a range of issues that we consider to be especially important for you to understand as empowered users of these systems. We will begin this discussion with the top row, the group of which we are calling AI performance errors, problems that arise due to inaccurate or erroneous outputs from an AI system. The most straightforward cause of AI performance failures are what we call traditional model errors, errors due to an overall inability of the AI system to effectively solve its task. The reason we include this category in this slide is a couple-fold. First, to remind you that no model will ever be perfect, just as no human is, so you should always be on guard for these. And second, to discuss that some tasks are simply harder for AI systems, and this does not always line up with how difficult a task is for humans. On the right is a chart we've made with some general heuristics to help guide your intuition for what tends to make a task more challenging for an AI system, at least as of 2024. As we work toward our presentation of other forms of AI performance errors, it's extremely important to understand that unfortunately, even AI systems that appear to have excellent overall performance, particularly during model development, may not generalize to all of the prospective use cases that we care about. A key task of ours as users and developers of AI systems is therefore to anticipate, assess for, and mitigate the effects of more subtle AI performance errors that may arise in slightly different settings. In the next section of this presentation, I'll use an extended example to introduce some of the challenges for generalization that arise in AI systems, and this will set up to discuss more subtle causes of AI performance errors like dataset shift and algorithmic bias. Along the way, this example will also provide us with a built-in review of some of the basic principles of AI that we introduced in the first lecture. Okay, so here we go. Let's pretend that you're a clinical researcher running an IT department at a major medical center and have been tasked with developing an AI to detect hip fractures. Naturally, the first thing that you're going to do is gather a whole bunch of hip x-rays, along with their labels, or the diagnoses assigned by radiologists. Next, you'll design a machine learning model, probably a deep neural network. This model will be trained via supervised learning by exposing it to all these pairs of images and diagnoses and trying to drive the model to learn the patterns necessary to be able to detect fractures in any new X-rays submitted as inputs to the system in the future. So far, so good. As you train the model, you intermittently assess its ability to make the correct diagnoses on the images with which you're training it, and you see that that capacity is going up, up, up. You've also set aside a subset of the images and deliberately chosen not to expose those to the model during training, so that you can check at the end to make sure that it hasn't just memorized the images in the training set. And the model does well on those too. As an aside, that process is called model validation, and if the images that you're using to validate or test the model are coming from the same hospital as the training data, it's called internal validation. Now, if you were the developer of this model, what might you do next to test whether it's really able to make these diagnoses? One option is to proceed to so-called external validation by testing the model further using radiographs obtained from a different hospital institution. Let's say we've done that and the performance remains strong there as well. Now for the big question. We've shown that our model is able to perform well on this task of assigning radiographic diagnoses to these hip x-rays. But what has our model actually learned to see? As a human, we would typically assume that the model has learned to detect fractures by visualizing the changes in the bones. This is, after all, what would seem to be the most obvious solution to the problem which the model would look for. But is there anything that guarantees that that is what the model is doing just because it shows strong performance? Perhaps surprisingly, the answer to this question is actually no. For while the model has only been shown hip radiographs, there's still no a priori guarantee that the model is looking inside of the bones to detect fractures the way humans would, rather than looking for some other features in the image that happen to correlate, on average, with a fracture being present. So how do we know what the model is actually looking at? As it turns out, with current deep learning methods, it is not currently possible to definitively answer this question, although we can do some clever experiments to give us an idea. In their paper in Nature Digital Medicine, which is the source of the images for this case, Badgley and colleagues developed a deep learning model for hip fracture detection on radiographs, just as we've described, and as we've seen, demonstrated solid performance both on images from within their hospital as well as external samples from another institution. But rather than stopping there, they decided to conduct some clever experiments to try to determine what it is that the model was learning. The researchers gathered a whole bunch of clinical variables that were not about the fractures themselves, but were potentially correlated with the presence of a fracture. Things like patient traits, such as the patient's age or body mass index, hospital process variables, such as time of day or day of the week or the wait time before the scan was obtained, the model of the scanner used to obtain the images, etc. And then they developed a test set where they intentionally sampled data so that these things, which would normally be correlated with fractures, were not correlated with the presence of the fractures in that test set. The variables that they used for this special sampling are here in the middle of the slide. They then retested the model accuracy on this specially balanced set of images and discovered that the accuracy of the model dropped when matching on all of the variables to roughly that of a coin flip. This proved that the model wasn't actually looking at the fractures themselves, but was rather looking at some combination of these features, which were somehow visible to the model within the X-ray itself, and using that to make its predictions about the presence of a fracture. While it may be initially unintuitive that the deep learning model detects and utilizes so many clinical variables from just within the radiograph itself, it isn't too surprising that they correlate with the presence of a fracture. For example, if you have an 80-year-old who's rushed into the hospital in the middle of the night and imaged on the portable X-ray machine at bedside, this situation likely carries a higher probability of a fracture being present than a young patient who arrives in the middle of the day and is able to walk down the hall to the non-portable scanner. The question for you as the hypothetical IT leader in this case is this a problem for us as an institution that would like to use this deep learning model? Or is it simply an academic novelty to see that it's not detecting fractures the way we would? The answer is, it depends. This model has high accuracy, but that accuracy has been shown to depend upon the presence of features in the image that are not the fractures themselves and only correlated with it. If those clinical and hospital process variables upon which it is relying remain present and correlated with the presence of fractures, the model will continue to succeed. However, if any of those variables change, either because the model is operating on a new population of patients, or because there's a change in the workflow at the hospital that changes one of those variables or relationships to the data, for example, if they purchase different scanners, the model may fail catastrophically. What we have in this example is the setup for a phenomenon called dataset shift. Dataset shift occurs when the input data to an AI system comes to differ in key ways from the input data it was exposed to during its training, potentially resulting in a deterioration in model performance. On the right, we have the image from a paper in which a series of machine learning models were tested on data from a hospital that underwent an IT upgrade in the year 2008. The models had been trained using data prior to 2003, and as can be seen, demonstrated strong performance in each year up until the year 2008, after which they demonstrate a sudden loss in accuracy. This was due to the fact that the models depended on specific idiosyncrasies in which the IT system stored its data. Of note, other models tested in this same analysis were robust to the changes in the IT system. Dataset shift can occur due to any number of changes in the input data to an AI system. For one potential categorization of types of dataset shifts for clinical models specifically, you may check out a paper from some colleagues and I in which we offer the categories of changes in technology, changes in population and setting, and changes in behavior, along with a bunch of citations and examples of these different sorts of shift. But here's the important thing. No AI system can be robust to every possible change. It's therefore imperative for model developers to consider potential shifts that could occur around their models and ensure that their models are robust to them. Similarly, it's imperative for institutions deploying models to have rigorous monitoring systems in place to ensure that their accuracy remains consistent over time. And finally, it's essential for us as clinical users of AI systems to be mindful of the settings, the populations, and the technology with which the model was developed, and consider how it relates to the settings, the populations, and the technologies in which we are applying the model in our daily use. Related in some cases to the phenomenon of dataset shift is algorithmic bias. Algorithmic bias can arise when the failure of an AI system to generalize disproportionately affects a vulnerable population. For example, on the left we have an image from a figure studying the performance of AI systems in dermatology. While the paper found that the AI systems boosted diagnostic performance across all populations studied in the analysis, due to disproportionately strong performance on light skin tones, the disparity in diagnostic rates between light and dark skin tones worsened with the addition of AI rather than improving. On the right, we have the performance of a model for predicting mortality in an ICU setting, which demonstrated higher error rates for females in specific ethnic groups. Now, I recognize that there's a lot of words on this slide and I don't expect you to commit them all to memory, but the purpose of this slide is to demonstrate that algorithmic bias can arise at any stage of the model development process. And I do love this figure because the authors visually depict the full data gathering and model development process to build a machine learning system, and notice and name the opportunities for bias that arise at every step along the way. Do consider reading through this slide carefully on your own time, as it may help galvanize both your understanding of the machine learning development process, as well as elucidate the process through which algorithmic bias can creep into these models. But again, the terminology itself is less important than the general concepts. So I hope that by this point I've convinced you that it's important for the users of AI systems to be as informed as possible about the data that went into their development, as well as the specific settings in which the models were built and tested. This raises the question of how we as clinical users are to access this information. Resources available for many AI tools include so-called model cards or model facts sheets, with an example on the right, which contain key information necessary for the thoughtful use of these models in practice. Many countries also have policies at various stages of development that require that this information be made available for clinical users. However, much of this is still a work in progress and will vary by location and institution, so it's important for you to look into the specifics of your models at your institutions. So we've now gone through in some level of depth this top row of pitfalls for medical AI systems, which tend to relate to AI performance errors or failures of generalization. For the remainder of this lecture, we'll go through this second row, which we term AI externalities. AI externalities is a term that we're using in this lecture to refer to pitfalls that arise directly due to a model's deployment, rather than secondary to errors made by the model. Examples include issues with model access or misuse, negative impacts of the AI on the human cognition of those using it, environmental impacts of the models, and privacy and security issues. Let's dive into some of these. Access and use case. AI models may be sufficiently accurate and still cause harm if they are not deployed equitably. One category of inequitable model deployment is the obvious one of access. For example, a model may have been carefully developed and have perfect performance across a diverse population, and in theory therefore show promise to decrease health inequities, only to worsen those same inequities if it is only accessible to wealthy populations. Slightly more subtle yet equally damaging harms can be caused by poor use case selection and problem formulation. For example, on the right, we see the output of an algorithm that was developed to identify patients in need of high-risk care management services. The model was intended to be used to flag patients who had high medical complexity and would therefore benefit from additional services. But the model was not trained to predict medical complexity directly, but rather was trained to predict high future medical cost, an easily available proxy for complexity. And due to unequal access to care, Black patients in the training set had received less medical care at a given level of complexity. As a result, the model was systematically much less likely to predict that a Black patient would be at high risk for future medical care needs, effectively requiring Black patients to be sicker before being flagged for additional resources. According to the researchers who published this analysis, correcting this error in problem formulation would have increased the percentage of Black patients who received additional help from 17% to 46%, a massive difference. This underscores how essential it is to consider AI use cases extremely carefully, as even an accurate model can cause direct or indirect harm to patients if the use case and problem formulation are inappropriate. AI models may also have unintended impacts on human cognition. Now, this is a very broad field of research, and I'm only going to give it a very cursory coverage here, but a few examples include automation bias, which is a human propensity to follow automated suggestions even if they're incorrect. This is related to more general blind obedience or authority biases. On the right, we have the results of a study examining the impact of automation bias in the field of radiology. While inexperienced radiologists and trainees were shown to be more affected by automation bias, radiologists of all skill levels were shown to be susceptible to this phenomenon. Recent work in a phenomenon known as induced belief revision has gone further and found that repeated exposure to AI systems may induce enduring changes in clinical judgment and practice. In other words, clinicians' own internal formulations and thought processes around specific medical phenomenon may be changed over time simply as a result of repeated exposure to AI systems' outputs. And since human labels are typically used as the gold standard for training future AI systems, AI-induced changes in human cognition could end up feeding back into future models, leading to something of a vicious cycle. An additional theoretical risk of AI deployment, especially over the long term as systems grow increasingly accurate, is that of de-skilling of humans, meaning that as we increasingly rely on AI systems to perform specific tasks, humans may lose the capacity to do them. While on the topic of the impact of AI systems on human cognition, I also wanted to add a brief word of warning about the so-called explanations that many AI systems attempt to provide for their decisions. As a general rule, particularly for deep learning systems, these should be treated with a fair degree of skepticism, as they are typically post hoc and may be misleading or inaccurate. A third category of potential AI externalities is that of environmental impact. Now, there's no question that AI models can cause significant environmental harm. They have significant data and energy requirements, and in particular, the upfront training cost of frontier large language models can require thousands of metric tons of CO2. However, it's also worth keeping in mind that existing hospital processes are extremely environmentally costly, And as such, medical AI models could also have the potential for environmental benefit through increasing hospital operational efficiency, minimizing waste, avoiding unnecessary procedures, decreasing staffing, and having similar effects. Therefore, the net environmental impact of a medical AI system will be use dependent, and in general is not an area of research that has received a lot of rigorous study. Finally, AI models exacerbate existing risks in data privacy, security, and manipulation. We will discuss privacy in some more depth in our large language model lectures, but it's important to keep in mind that AI systems, especially language models, may memorize and regurgitate large chunks of their training data, and that commercial models like ChatGPT continue to train on input submitted to them by default. So it is extremely important to be wary of privacy concerns with these models and to not submit sensitive data to models that are not private and approved by your local hospital. Adversarial attacks are another phenomenon to be aware of, in which the user of an AI system may attempt to craft the data they submit to it in order to force it to produce a desired response. At this point, we have now discussed this full framework for the pitfalls of biomedical artificial intelligence. While the framework is not comprehensive, we do urge you to keep these principles in mind as you become a user of these systems. In our next lecture, we will begin our more comprehensive introduction to large language models.